Hello, all. This is Team One's 3-minute thesis for engineering practicum. Today, we're going to be going over Chapter 2 and Chapter 12. Starting off with Chapter 2, the Chapter 2 focuses on selection of materials and processes. So, just as a brief introduction, an integral part of design for manufacture is the early selection of materials and process combinations. This is important because decisions made early on can affect cost effectiveness and opportunities for major improvements later down the road. So, our one question to answer for you is, what's the best method to select materials and manufacturing processes to develop the best product? Now, getting into the selection of manufacturing processes, once the overall function of a part is determined, a shopping list can be formulated. And things you will want to include on this shopping list are geometrical features, material properties, and the final functions. And as discussed in class, we know a little bit about the design for manufacturing assembly. So, one goal of this analysis is product structure simplification and part consolidations. In other words, you want to try to make the part as simple as possible, which, there are a few ways you can do this because many combinations of materials are not possible. Many combination of processes are not possible. And these processes can be categorized as either one of three things. Primary, which is used for producing raw materials and is also used to make the main shape. You have primary/secondary processes, which can generate the main shape of the part, and it also includes removal of material, such as if you 3D printed a part, that would be you removing the support. And last is tertiary, which doesn't affect the geometry of the part and it always happens after the primary and secondary process.
The systematic selection of specific materials to meet required properties is given considerable attention. Today, numerous textbooks, handbooks, and online databases of material properties are available. However, their usefulness at the very early stage of product design, when initial decisions on materials and processes are made, is restricted because the material selection is considered independent from the manufacturing processes that may be used. However, several approaches can be adopted to rationalize the search for suitable materials for application during early product design. One of the approaches that the book suggests is grouping materials into process-compatible classes. Rather than using a single comprehensive materials database, it is preferable to divide the material databases into classes related to the principal shape-generating processes used in discrete parts manufacture. This is necessary because the selection of processes and materials must be considered together. The other approach that the book suggests is selecting materials by dimensionless ranking. Material selection requires comparison on the basis of total performance, best performance per unit weight, or best performance per unit cost, etc. The procedure for making these comparisons on a dimensional scale from 0 to 100 will facilitate selection. For any property, the highest and the least value are assigned 100 and 0 in that database. To learn how to use this approach, the book gives us an example. Suppose we want to compare different values of young modulus. The largest and the lowest value in the database is likely to be the value of diamond and natural rubber. We plot our values in the equation, and what we have left is the young modulus of the material that we are looking for.
Next, we're going to talk about sand casting. So sand casting is a process in which molten metal is poured into sand molds, which are broken away from the casted part after the molten has solidified. So some of the basic characteristics in mold preparation, the sand is typically made of 88% silica, 9% clay, and 3% water, and it is mixed evenly to disperse the clay additive. This is important because you want every mold to have the same properties. In most foundries, sand may be reused after it is cleaned. It's also important to note that almost any metal can be sand cast. So you can see in table 12.1 that ductile iron, gray iron, aluminum, and magnesium have excellent castability, and this refers to the amount of shrinkage that takes place as well as fluidity. and the temperature range over which the metal solidifies. So the gating system consists of a series of channels and reservoirs designed to feed the molten metal to all parts of the mold cavity. First, the molten metal enters the mold through the pouring cup. It then travels down the sprue and into the sprue well. The runners deliver the metal to the gates, which open the mold cavities, and then the runner well and runner extension capture the early metal flow, which degrades the metal properties. The different type of patterns you can use to form sand molds can be made of wood, metal, or plastic. Hardwood and plastic patterns you can use for low production, and then cast iron patterns you can use for high production. They're commonly made into two pieces split along the parting line of the casting, which you can see on the left under B. And the sand mold is created by compacting sand around the pattern. Machine assistance is usually used to pack the sand as densely and homogeneously as possible. So after the molten metal is poured and then it is cooled, you have a casted part. So we want to say thank you. The roles for the team: Myra Myers was responsible for selection of manufacturing processes. Anna DeLeon was responsible for the selection of materials. Kayla Oden was responsible for design for sandcasting. And Samuel Silvera was the transcriber.